Last episode, we built a transformer that read movie reviews and beat the LSTM at telling good from bad. It could judge text, but judging is the easy half. Today, we ask the harder thing: can the same machine write? We're still living in the train and predict stages of our pipeline, but this time, the predict step is the whole show. We're going to teach a model to generate original text and hand you a single dial that controls how wild it gets. We'll train it on Shakespeare. Here's the trick that makes generation possible, and it's almost insultingly simple. The model only ever learns to do one thing: look at some text and predict the next token. That's it. To write a whole sentence, you predict one token, glue it onto the end, and feed the longer string right back in. Predict, append, repeat. That loop, feeding your own output back as input, is called autoregression, and it's the entire engine behind every model that writes. So, how do we train a next token predictor? You'd think we need a labeled dataset of here's the right next word. We do, but we get it for free. Take any sentence. The input is the sentence. The target is the same sentence shifted one position to the left. Every character becomes a tiny lesson. Given everything before me, here's what came next. The text labels itself. That's why you can train these things on the raw internet. No humans tagging anything. But there's a catch, and it's a sneaky one. During training, the model can see the whole sentence at once, past and future. If we let it peek at the future, it cheats. Predicting the next character is trivial when the next character is sitting right there in the input. So we blindfold it. Causal masking, also called a look-ahead mask, lets each position attend only to tokens on its left, never its right. It has to predict the future without seeing it, exactly like writing does. Now the model is trained, we feed it a prompt and it hands back not one answer, but a probability for every token in its vocabulary. The lazy move is to always grab the single most likely one. Do that, and the model gets stuck in loops. Do. Instead, we sample, we roll a weighted die, where each token's chance of being picked equals the probability the model assigned it. Likely tokens win often, rare ones sometimes sneak through. That little bit of chance is where originality comes from. And here's the dial. Before we roll the die, we divide the model's scores by a number called temperature. Low temperature, say 0.2, exaggerates the gap between likely and unlikely. So the model almost always picks its top choice, safe, fluent, and a little repetitive. High temperature, 1.2, flattens the differences, giving rare tokens a real shot. Adventurous, surprising, and eventually unhinged. Temperature 1 leaves the probabilities exactly as the model learned them. Watch what that does to Shakespeare. At temperature 0.2 you get the king is the wind of the world, grammatical safe, slightly hollow. Crank it to 0.8 and you get O gentle traitor, what new sorrow climbs the night. That's style, that's the sweet spot. Push to 1.2 and it shatters into fraud, bless and mirth, quack. The dice are too loud, spelling itself breaks. One knob, the whole spectrum from boring to broken. And if you watch a model train, you watch a child learn to write in fast forward. Early on, it produces letter soup, then it discovers spelling, real words appear. Then grammar, the words line up. And finally, faintly style, the cadence of the thing it was trained on. Nobody programmed any of those stages. They fall out of one objective, repeated billions of times, predict the next token. And that, scaled up almost beyond comprehension, is exactly how ChatGPT works. Same loop, same masking, same sampling, same temperature dial. The difference is size and data, not idea. But so far, we've only predicted text in one language. Next time we teach a model to read in one language and write in another. Machine translation from sequence to sequence all the way to the transformer. Let's build it. The script is 3 short screens. First, load Shakespeare, turn it into integers, and slice it into input target windows with a tf.data pipeline. then a causal transformer block, and the assembled model, then the training run and the generate loop with our temperature dial, every line on screen. First the data, we load the Shakespeare text file and grab the sorted set of unique characters. That's our vocabulary, about 65 symbols. We build two lookup tables, character to id and id to character, then encode the entire corpus into one long array of integers. Nothing fancy. Char level keeps the vocab tiny, so this trains on a laptop. Now the windows, we wrap the integer array in a tf.data dataset, batch it into chunks of sequelen plus 1, and for each chunk we split it into the input, everything but the last character, and the target, everything but the first. That one character shift is the self-labeling we talked about. We shuffle, batch and prefetch, so the GPU never waits. Next screen, the model. We define a transformer block as a Keras layer, a multi-head attention, a feed-forward subnetwork, two layer normalizations and residual connections. The crucial argument is use causal mask true on the attention call. That's the look ahead mask in one flag. So position I can never attend to position I plus 1 or beyond. We assemble the full model with the functional API, an embedding to turn token IDs into vectors, a positional embedding added on top so the model knows order, our causal transformer block, and a final dense over the vocabulary that scores every possible next character. Then we compile with the Adam optimizer and sparse categorical cross entropy. Sparse because our targets are integer IDs, not one-hot vectors, and from logits true because the final dense emits raw scores, no softmax. Training, we call model.fit for 30 apex over the dataset. Watch the loss in the terminal. It starts around 3.1, where the model is basically guessing among 65 characters and slides down past 1.4 as it learns spelling, then words, then rhythm. Lower loss literally means better next character guesses. And the payoff, the generate function. We start with a seed string, encode it and loop, feed the current sequence in, take the logits for the very last position, divide them by temperature, and use tf.random.categorical to sample one token from that distribution. We append it, slide the window, and repeat for as many characters as we want. 3 calls, temperature 0.2, 0.8, and 1.2. Give us the 3 columns of verse you see in the figure. Same weights, 3 personalities. That's a working writer, one objective, predict the next token, plus auto-regression, causal masking, and a temperature dial, and you've got the beating heart of every large language model alive. Next episode, we keep the transformer but give it 2 languages. We'll build machine translation, starting from a sequence-to-sequence encoder-decoder and ending at the transformer that powers Google Translate. See you there.